All right. Thank you, Bill. As Bill said, my name's Todd McKinney. I'm from the University of Alabama in Huntsville. It's really great to be here. I've been involved in a lot of different ballooning projects, both pico balloons and latex balloons, which I'll talk some about. But today we're going to talk about the solar eclipse and some awesome things that students at the University of Alabama in Huntsville under the Space Harbor Club did during the solar eclipse. So let's get into it. So I just want to, say what the Space Harbor Club is because it's a really, really great group. Basically, it's fully student-led. There's many different projects, so I've kind of listed the projects up here. There's AutoSat, which is like rovers and autonomous payload competitions. BalloonSat, which I'll talk a lot about today. Rocketry, it's Space Harbor Club. You have to have rockets, right? And spaceflight. This is actually a newer project where they're working with NASA to send some satellites up, so it's really exciting. And then we have this program called 2 Month, which essentially gets young freshmen involved. We kind of pitch them a challenge, and they come up with their own designs and stuff. So it kind of teaches like STEM kids, the benefits of pursuing like a STEM career. So that's a great program. So now I want to talk about the solar eclipse. So Space Harbor Club, we participated in the solar eclipse, many different projects. Over 28 University of Alabama and Huntsville students participated. So this is a picture of the team out in Illinois, where we went for the second solar eclipse. So we all drove out there and we launched a bunch of balloons, which I'll talk about in a second. So it's a great, great group of students and things I'm going to show. It's really, it's not just me, it's everybody in the team putting in a lot of work to accomplish some cool objectives. All right, so I want to talk really quick about some of the things we did during the solar eclipse, specifically some of the science that we wanted to understand. So the first one, has anyone heard of shadow bands, eclipse shadow bands? Right, so if you saw their solar eclipse recently, you probably noticed these little bands of light right before and after totality. So basically, it's this hypothesis that the Earth's refractive index is causing these wave patterns right before the moon fully covers the sun. So there's been experiments in the past, specifically from 2017, but we wanted to build a whole project to understand shadow bands. So it's really exciting. So basically, when we went to the drawing board, we wanted to make this instrument, we call it the SBI, to understand the frequency of these waves. So basically, our thought was we have these light sensors on 4 corners, right? And as the shadow goes across the board, it can be picked up by these really high-resolution photodiode sensors. So we can characterize the size and frequency of those little light oscillations. So that's the drawing board. We ended up building custom PCBs to do this, right? So this is the top of the payload, the bottom of the payload, and then we have this mounted on a line because we are going to fly these, and we did fly these on balloon payloads. So you can see these are the 4 photodiodes that I mentioned. And then we have a Raspberry Pi that's running everything, as well as some batteries. And then, of course, we have our standard atmospheric measurements like temperature, pressure, humidity. It also, we installed a GPS with a little patch antenna. So the photodiode data saved really, really quickly. I think it was 60 hertz, whereas the GPS data we saved at 1 hertz. So again, all custom-built hardware by students, right? So I think that's pretty cool to be able to say that we can do something like that. So this is our concept. This is kind of funky. We wanted to build a bunch of these, right, and fly them on a really long balloon line, because essentially what we're trying to do is we're trying to get a profile of the atmosphere. So I have this little funny cartoon here. As the balloon line is rising, we have some reference height here. Each of these payloads is going to sample that altitude, right, as it's rising up. So you can essentially get a really cool profile of a particular altitude with a really long balloon line with different sensors. So this is kind of fun. If anyone knows the height of the Saturn V, if anyone's been to Huntsville, Alabama, we have the Space and Rocket Center, we have the Saturn V. This is the scale we went for the balloon. This is one of the longest lines we could possibly do. So we also put streamers on here so it's visible. And we also followed a NOTAM when we flew this. So this was a success. So these are some photos from the second solar eclipse. What we actually did, this is really cool. We actually flew one of them and we cut it down at 7 kilometers, and another one we left tethered on the ground. So you can see right here, this is the balloon with the little streamers up here. And we actually had this little triangle platform that was, holding the tethered balloon. And then this is some of our students getting all the different payloads ready. So this is pretty awesome that we accomplished this, especially we had to dodge our final schedule because we are students. So it's kind of like we were like doing all this work and building all these payloads. And we're still trying to study and get good grades. So life of the student, I guess. So we got back from the campaign for doing the eclipse. We have so much data to look at. It's making our heads hurt. We just got down with finals. So we're really excited to look at the data to see if we can look at these shadow bands in more detail. So those are some great photos. Again, I want to give this shout out to the team. They're great people. So I also want to talk about this. Me and a fellow student, Mason Mills, he couldn't be here today, but we built 4 radiation detection payloads. And essentially what this is a Geiger tube, right? We also flew a UV sensor, and as Bill kind of mentioned before, we have this PTH sensor here. So we flew 5 of these during the solar eclipse. We actually flew 4, and we left 1 on the ground as a reference. So we built all of these in like 4 weeks. We were kind of just sitting around a dinner table, and we're like, what if we flew Geiger counter in the solar eclipse? And then we rushed and we built them all. So it's kind of fun. So here's some data. It's probably a little small to see, but you can see right here, I want to point this out really quick. So these 2 plots right here are the UV and the light readings, and you can beautifully see, right, this is a time series plot when the totality happened. You have all 4 payloads were in the path of totality, so all the light readings went to 0, so that's a really good sign. We have some interesting radiation data, so we did see some spikes after the eclipse. We need to look at this in more detail again. But all 5 payloads worked great, and it was really exciting. So also, I want to show this. This is kind of a profile, and what I'm actually going to do, this is some data here. It's fun to look at, but I think it'd be more interesting if we looked at this video. So let me see. I'm going to pull up a little video, see if this will work. Just look it up. Give me a second. It's always the technology. All right, I'm going to show 2 videos. And the first one, and again, this is all on YouTube, so anybody can search this up. Again, we are the Space Harbor Club. And is it showing up? Hold on. I think they have this on presenter mode. Duplicate these displays. Keep changes. All right, can y'all see this? Good. So this is really cool. Again, Space Harbor Club YouTube channel. We're trying to be more active on this YouTube page, include posting balloon videos. So it's kind of cool. So I really recommend y'all save this and kind of check some things out. So the first thing I'm going to show is this is really neat. So this is the Geiger counter payload. We actually flew GoPros on this flight as well. So, and what we did was for our custom-built payload, we basically had this software that we kind of modified to put the flight data over the balloon data or the balloon video. So this is one of the videos. It's really cool to see. So see if our internet can keep up with this. I don't think so. Let's do 360. So this is really cool. So what you're seeing here is the GoPro video here, and then we actually have all the telemetry data from the flight. So this includes temperature, pressure, humidity, wind speed, direction. And then we also have this altitude versus time curve up here. So that allows you to actually look at the video and actually know where you are during the flight instead of just saying, oh, you know, I'm up here. So what I can actually do is I can skip to when the shadow appears. So you can see that, you know, over the horizon, you can see that it's slowly getting dimmer. And then this is actually the totality. So the balloon is in the path of totality, which is awesome. So we were really hoping that the wind wouldn't blow it out of the path of totality. So the winds were perfect for this day. I also want to note, so this bottom right-hand corner, this is kind of funny. This is the Geiger counter. So every time, you know, you're looking at this value, you know, everyone knows what a Geiger counter is, right? It's the beep, 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 beep. So this is actually doing like 11 beeps per second because you're getting out of the atmosphere, right? And you have all these cosmic rays that don't get to the surface, and it causes our Geiger counter to go crazy. So we're at like 12 beeps. I think like at 15 kilometers is like the same amount of Geiger counter beeps as you would have at Chernobyl, you know, the site. So that's kind of a cool fact. The atmosphere helps us, you know, it's very useful. So this is a great video. I recommend y'all check it out. Space Harbor Club YouTube channel. Yeah. So the other thing, let's keep going here. Now we're in this mode. So this is probably our best video we've ever taken, ever. This was such a good flight that it actually got posted on the NASA Sun in Space Twitter page. So here's some photos. I thought that was really cool that our school got kind of, you know, advertised by the work we did. So I'm going to go ahead and show this video. This is probably, this is just fun. And it's a great video. We play this at tabling events. When we do STEM events, we also, we have like a VR headset. So we like to say, like, you know, you're watching a 360 video and you put a VR headset on, you can like look around the flight. It's really, really cool. So this, again, when I say 360, it means that it's interactive. So you can look around the balloon flight as it's happening. So the balloon's up here. You know, this is right at launch. And, you know, this is the whole team. So it's really, really cool. So we can, let's go ahead and skip to the shadow. So this is right when the shadow was coming over the horizon. So you can see we have the balloon up there. Look how much bigger the balloon got. That's funny. And then this is all our, you know, our class and project stickers. You know, it kind of flew on the maiden voyage. So there's the, you know, the shadow. So it's really, really cool. I also kind of like to show, let's see if I can get it. So this is the balloon burst from the 360 camera. Let's see. So now, and I want you to notice how steady the video is still, right? I mean, the payload's going crazy, but the 360 camera has a really good system for stabilization. So, which is really incredible. Let me see if I can adjust this even just for a little bit. This Wi-Fi is struggling. There's so many people, it doesn't know what to do. So yeah, very, very cool. I'm going to show that. That's all our logos. It was a really, really, really great day for this. And we had clear skies to see the solar eclipse. So a bunch of college students having a trip paid for to go see the solar eclipse. I think that's a really good experience of itself. So we're very, very happy for that. All right. Well, I think that is it. So I want to conclude this part of the talk. The conclusion is, you know, Space Harbor Club members, we did it. It was a really great time, a lot of great friendships made. But of course, you know, we did the flights. There's still a lot more work to come. I mean, when you have such a successful project, especially when you're talking about science. You got to look at data now, and you got to see like, oh, well, what was the whole point of the project, right? So lots of data to look at, and hopefully we'll get some publications out and get some student names on peer-reviewed work. So that's kind of the goal. You know, it could really help their resumes, help them get a good career and everything. So thank y'all. Got a question here? From the video? No, no one did that. But that's a good idea because, I mean, you know how high you're up, so you could calculate. Because in some of the frames, I mean, you can literally see. I mean, it's almost like you can see the full thing. I think Bill showed that photo as well. I mean, it's literally, you could definitely do that if you know your altitude. So that's really cool. Yeah. Any other questions about the Eclipse balloons? I'm sorry, I can't hear you. Right at the tip. We actually were originally going to go to Texas for the second solar eclipse, but if y'all remember, the weather was not looking good for clouds in Texas. So we had a friend of ours who actually had a golf course. So literally last minute, we just drove to Southern Illinois and slept on a golf course. You know, so anything to see that, you know, totality, you know, we would have driven to Maine if we had to. You know, that would have been a far drive from Huntsville, Alabama, but I think we would have done it if, you know, just to see it. So any other questions about Eclipse balloons? All right. Oh, we got, is that one right here? Yeah, so that's a great point. So that's data we still need to look at because you're right. The balloons that we flew were launched at different times, so they're, you know, different positions downrange. But the one thing I do know is, you know, we were launching right in the center of the path of totality. So when the shadow came across, right, like they were all in the path. But you're right. As the, you know, the moon shadow is approaching, one balloon's going to encounter it first, based on, you know, the position. So that's a great point to look at that data. Yeah. So in total, we flew 4 normal latex balloon flights. So that's just the balloons that go up, burst, come down. Each of those had their own GPS trackers, APRS trackers. And then we also had the tethered flight that I talked about. We didn't launch that one, but it just kind of sat there during the whole eclipse. And then the other one we launched it. It's a really long line, and we cut it down at 7 kilometers. So in total, that's 6 balloons that we flew during the solar eclipse. So it was very hectic because, you know, most balloon launches, it's kind of like, okay, we're going to launch when we're going to launch. But we had a deadline. That moon was coming. And if you miss it, like, you missed it. You got to wait. When's the next one? I don't know, 20, 30 years. Yeah. So in total, I think I mentioned this, we left 1 radiation detection payload on the ground as a reference, and then we flew 4. So in total, there were 5 payloads. Yeah. So that's a really good point. I'm glad you noticed that. So, you know, the data we looked at originally, 2 of them had that spike, but the other 2 didn't. So that kind of aligns with the question he asked: where were those 2 in relation to the other 2 balloons where we had that spike? What's really cool as well in the 2017 eclipse, before you know, I was at University of Alabama in Huntsville, they flew 1 single radiation detection payload in 2017, and they actually saw that too in 2017. So there might be something interesting going on. So when we look at the data, it might be something we can actually do with that. Yeah. Yeah.
Wanted to interject just for a minute. Todd goes out with a group of students to not chase, but study tornadoes, hurricanes, and they launched with this big $1 million van filled with radar equipment. If you see Todd's vehicle with the radar in your front yard, head to your storm shelter immediately. But they launched a weather balloon with APRS in the eye wall of Hurricane Ida. And I clocked the first reading I got from APRS FI was 80 miles an hour, and it was 200 feet above the ground. And when they launched it, they brought it out of the van and let it go, and it went, it just disappeared instantly. It was like a mile away, like in a minute.
I figured, I'm young. You might as well live a little, right? All right. Well, is it okay, Bill, if I go on to the next talk? 30 minutes. Excellent. Okay. So this is really exciting. So this is, I just talked about the Eclipse. We had 28 other students working on that project. This is kind of my personal project that I've been working a lot on. So the way I actually met Bill was through pico ballooning, right? So I've always kind of been interested in ballooning. But I love the pico balloons because you can launch it and you can watch and see where they go, and they can stay up a while, and it's kind of personal, right? It's like, oh, my balloon's over Europe, or so it's really fun. So I wanted to essentially, as an atmospheric science major, PhD student at the University of Alabama, Huntsville, the pico balloon hobby, right now it's a hobby, right? So you fly these and it's fun to watch, but can this data be used for science, right? Can it be used to improve weather models? And those are the questions I kind of asked myself. So I ended up building this resource that is specifically for pico balloon data and getting data out to people and to scientists and the students and stuff. So I think we all already know what pico balloons are, as Bill talked about, but this is a great photo that kind of compares. Bill was comparing it to the latex balloon. You can see the difference. You have your nice, National Weather Service latex balloon, and then I call this the Walmart bag whenever I show this photo, because it literally is like a Walmart bag. So the obvious difference is, this balloon goes up, bursts, comes down, and then this balloon stays up at one altitude and floats, right? So these balloons can remain aloft for a very, very long time, years, sometimes months, of course. So that's kind of useful, right? If you can track something and know where it's going in the field of atmospheric science. So I want to introduce this. This is really exciting. So this is a website. I'm going to put the link right up here. This is the picoballooonarchive.org, what I, introduced, and I'm going to do a little live demo of this website in a second. But this is designed to use pico balloon data for weather research. So people, all around fly these balloons, and data's just sitting out there, right? So let's grab that data, put it somewhere, and do some stuff with it to make it usable for research purposes. So this is a great figure that I did of how does this website work. So this is kind of your classic figure. You have your pico balloon floating between 9 to 15 kilometers. In this case, for over horizon transmissions, we're talking about HF. So you have all these whisper stations, right, that are listening for these frequencies. They can decode your frequencies, post that data to the internet, and then we have some other scripts that can process data, push it to a website called aprs.fi or SondHub Amateur, which is kind of like a really big ballooning site for a lot of different people that are into ballooning. And then our website, what it does is it downloads data from both those sources, both Whisper, APRS, and SondHub, downloads that raw data, and it basically standardizes all the pico balloon data into a single file format. So instead of, people launch these balloons and they might be sending something different, or there's different file formats. When we're talking about atmospheric science research, it's so much better when everything is in the same format. It's less of a headache for scientists, because scientists would rather be doing the science than trying to configure files. That's what it comes down to. And then what I do, I'll show you in a second, there's some charts and some quicklet plots, and then we have, just the archive that people can download the data from. So I'm going to do a live demo now. Let's see if this is going to show up. Okay, he disabled my thing again. Stand by. Hold on a second. Nope. I think I broke it. Stand by. Okay. All right. Duplicate these displays. Here we go. All right. Always the tech. Okay, so this is the website. Again, I put this website link up. Anybody can go to this. This is publicly available to everybody. It's peakaballooninarchive.org. So it takes you to this website. The homepage is, some photos, some, information about the archive. We also have an Amazon web server. So the data is also sent to this kind of classic, data repository. So, this is kind of everything I've talked about, how the website works and naming structures for the files. So this is really cool. So what I can do is I can go over to the archive tab, and this will give you a chart of all the current Balloon that are in the archive. It also tells you if the flight is occurring right now. So let's say there's a balloon up, you can see if it's in progress or if it's, quote, finished. Basically, the archive looks to see if there was data the last 5 days, and it says if it's finished or in progress. So, so that's really cool. So you have some date ranges, your total data points, latitude and longitudes, how long it's been flying, minimum, maximum latitudes, as well as if it has any other telemetry data like temperature, pressure. So what you can do, this is really cool. So I can click on this Quicklet tab, and it will actually pull up a custom Python generated plot for the Balloon. So it gives you wind speeds versus time, latitude versus time, altitude, and then your U and V wind components of the Balloon. So this is like a quick, I just want to look at the data really quickly, give me that. If you want to do something with the data yourself, I got you. All you got to do, if you click on the call sign, it will actually download a text file. So anybody can look at the data, if you want to put it in Excel, and it gives you, a header file of all the information, how many data points, how long it's been up, and it's all right there for anybody to use. So that's really, really cool. So let me actually go back to here, is kind of what I've just talked about. This is actually the file format structure. So I actually have this chart here that explains, in this case, I'm using the BS-43 balloon as an example. There's the payload type, right? We post both APRS and Whisper balloons to the archive. The total data points, how long it's been up. We also do this calculated number of circumnavigations kind of estimation, which looks for when it crosses, the start longitude, and it kind of does a running tally. Sometimes that's not right, because sometimes these balloons do weird things, and it's not really a circumnavigation, but it's close enough. And then we have headers and, of course, the data. So that is the file. And again, what's great about this is every single balloon in the archive is formatted like this. So if you want to download all the data on the whole archive, everything's the same format, which is really useful. Okay, so you can also, this is really neat, this synopsis tab actually kind of gives you a rundown of current flights in progress. So this was updated, this is UTC time, so this was updated today. Everything's automatic. This shows the current balloons that are in the archive that are still sending data. It's on a map. This tab actually shows you, this is the whole archive. And what we've done is we've colored this by wind speed for all the data points and float altitude. So you can see there's this nice jet stream over China, which is very prevalent. We've actually broken this up by spring and summer and fall and winter domains or seasons. So you can see all the data there. This also shows you some histograms of all the data, and this can also tell you how many balloons have been aloft, in the database. Again, this goes back all the way to 2021 when I did my first 3 Pico balloon flights. There's some other cool things, like if you want to look at latitude versus wind speed, right? Because remember, this is a global database. Pico balloons fly everywhere. So you can actually look at these mean, wind speed values, and then I'm actually doing a mean average off of spring and summer and fall and winter means. So look at this. You can see there's that big jet stream. So we can get, these balloons can move really, really quick in the jet. Really, really quick. So that's the synopsis tab. Again, this updates every day to show the current, status of the archive. So I like to call it an operational product, which is really, really, really great to have. All right, so let's continue. So I also want to talk about this because as a atmospheric scientist, as a scientist in general, we really want to see how well our measurements are doing. So what's unique about the Pico Balloon Archive is, as we all probably know, the WSPR grid system is not as small as like a normal GPS point that might have like 10-meter resolution. These WSPR grids are pretty large, right? Especially a 4-digit grid's really large, but a 6-digit grid is still pretty large, right? 2 to 3 kilometers. Are you flagging me?
Sounds good.
Okay, I'm breaking things up here. So what we actually do is we calculate a position error for the Pico balloon, because think about it, if you want to use this data for atmospheric research, let's say we want to look at like wind speed and wind direction measurements around the whole globe, we have to know and quantify how well that calculation is to be used for science, right? Because we all care about how right our answer is. So this is a calculation we do in the archive, which essentially gets a position error that looks at the width and the height of the grid squares as a function of latitude. And based off of that, we can actually calculate a velocity error, right? Because if we're looking at how fast these balloons are moving, we're assuming that's the wind speed. I want to know how accurate that wind speed calculation is. So this is the equation we use. This is the position error divided by the time, the change in time. And then we also get a wind direction error, which is basically the arctangent and the position error divided by the distance between those two points we're using for the calculation. Fastest I've seen, let's see, let me convert to miles per hour. I think it was 192 miles per hour. It was over South Korea. 102 miles per hour. The thing was cooking to get home. All right, so I also want to show this because this is more the science side on my part. So we have all these weather balloons around the globe. So I kind of wanted to see how well that calculation from these Pico balloons for the wind speed and direction was to the radiosondes. So I wrote a lot of code that it basically says if there is a weather balloon that has been launched within like a 50-kilometer radius, as it goes up, the Pico balloon's coming over. Let's look at what those two measurements are and compare them. So I have a bunch of code that looks at all the NOAA data and all the weather balloon data and finds that value. So it's kind of fun. So this is a good kind of one-to-one line showing the differences between the wind speed and direction, Pico balloon versus the weather balloons. So pretty good. We're very happy with these results. So the wind direction was really good with the R-squared of 0.78, so we're very happy for that. Okay, so I'm going to speed up a little bit because Bill already kind of talked about this, but Pico balloons are great, right? They fly, and you can track them, but what is really lacking is good temperature, pressure, humidity data, right? So we built this custom sensor that's kind of modeled off a radiosonde and to fly in a Pico balloon. It's really small, it's lightweight, and it can be used to send back pretty good data of the atmosphere from a Pika balloon. So this is our sensor that Bill kind of already touched on. We actually flew this on a normal weather balloon flight to compare it to a research radiosonde. So this is one of the National Weather Service radiosondes, and here's our two of our sensors. And we flew this just on a normal latex balloon. And we also compared it to these cheaper, BME 680s, which aren't really research-grade instruments. They're surface-mounted temperature sensors, which typically always have some warm bias. This is kind of a side note. I don't know why you would paint your PCB black, right? It's going to absorb all the sunlight. It's going to get hot. I think they just, marketing, it looks nicer for marketing, I don't know. But not good for temperature measurements, I'll tell you what. So this is just a quick comparison. Our sensor's pretty dang good compared to the $500 research radiosonde. In total, I think our sensor costs like $40 to make. So this is temperature, humidity, and pressure. And then we have these one-to-one lines here as well. So, we have R-squared values of like 0.9993. So we're very happy with the performance of the sensor. So we also flew one of these on a Pika balloon flight. I just want to give a big shout out to the Bottle Cap Balloon Brigade. They actually flew one of our sensors on the NE9JJ Pika balloon. So this is also on the archive when we actually built a custom plot for this. So you can go to the quick look and it shows actually the sensor data. So this is really neat. We also included a solar elevation angle calculation and some other things about sun flux to kind of look at the sensor data. So things we're noticing with these sensors, some challenges we still need to address. When you're on a Pika balloon and you're moving with the air, you're typically always going to have some sort of warm bias, right? Because when you're moving with the air, you don't have airflow on your sensor. So the sun is just heating up your sensor package. So we typically always see like really warm temperatures. And you can kind of look down here, this is, each individual day of sensor data. We can have a really wide range of temperatures between like 20 degrees. That is not what the true temperature is at that one altitude. What's happening is the sensor is rotating and is pointing away and towards the sun over and over again. So it's like you're stepping in a shadow and out of a shadow like 5 different times, and you're looking at how you feel. I'm warm, I'm cold, I'm warm, I'm cold. That's exactly what happens for these sensors. So we're working on a way to shield the sensor more from sunlight, maybe put it in some shade. But the key is you really want to make sure that you put it in a position where you can quantify what it's doing really well. Like I want to be able to say, I know my sensor is shaded, or you want to be able to say, I know my sensor is in direct sunlight, because maybe I could correct for that based off the solar elevation angle. So a lot of things are in progress trying to get good temperature, pressure, humidity data off of Pika balloons to be used in atmospheric research. So, okay, so some conclusions about that. I hope you all enjoyed that because this tool was built to give people data, right? It's built for people to use data, download data, look at the data yourself, do some scientific work with it. So that's the whole point of it. We're going to perform some more PTH tests, hopefully some more latex flights, Pika balloon flights. And I also included this up here. These are 3 papers that I wrote. If you're really interested in, Pika balloons for scientific research, this paper right here is using Pika balloons to evaluate weather models. So if you're interested in that, that's in BAMS magazine. This paper, if you're more in the ham radio whisper propagation stuff, we actually use Pika balloons to evaluate Antarctica radio propagation. We flew a few down in Antarctica. Some really interesting propagation results. I mean, we're sending signals literally all around the globe while over, the South Pole. It's kind of incredible. And this is a really great paper at the end right here. If you're looking to get into Pika ballooning yourself and you kind of don't know where to start, this is kind of teaches you the pressure testing protocol for these balloons. It's like a very nice methodology paper. So that's a great paper to go to if you want to learn more about trackers and stuff. And I also want to say right now, we have Bill Brown up here. His sky trackers are awesome. They probably send the best data out of all the Pico balloons. I'm not biased, I promise. Actually, I am biased, I'll say it. But literally, you know, every sky tracker that's flown that's on the archive sends really reliable data that has really improved the archive. So we have our resident expert right up here on Pico balloon trackers if you want to talk to him. All right, well, that is it. Ooh, you have it?
Board, anybody wants to see one, Todd can show you.
Yes, in the flesh, PTH board. So that is it. Does anyone have any questions? I want to thank y'all.